Differential Calculus 2017 question 10b. A spacecraft of mass m moves in a straight line towards O, the center of the Earth. The radius of the Earth is r. When p is a distance x from O, the force exerted by the Earth on p is directed towards O and has magnitude k over x squared, where k is a constant. Show k is equal to mg r squared. Okay, well, we're dealing with force here, and force is equal to mass times acceleration. And in this case, gravity is bringing it towards the Earth. The force at a distance x is k over x squared. Now we have an r in here, so the force at a distance r must be equal to k over r squared. So that's my force. So k, we can say k over r squared would be equal to mg. So then k is equal to mg r squared, and that's what we're looking for here. Part B, p starts from rest when its distance from O is 5r. Find in terms of r the speed, so we want v, of p as it hits the surface of the Earth. So what have we been given so far? The force is k over x squared. So the force is equal to k over x squared, and we've worked out k to be mg r squared. So mg r squared over x squared. And as the force and x are measured in opposite directions, one must be a minus. So this force is equal to ma. F is equal to ma. So we can let either side be a minus. So our force is minus mg r squared over x squared. We let that start as the minus. That's equal to m times a. And we know that a is, to get my v in, is v dv dx for my acceleration. So if we can simplify this, we should be able to get the speed of p in terms of r as it hits the surface of the Earth. Now, it's starting 5r above. If we put the 5r here, 5r above the center. So this is going to be the distance r here, and the distance 5r here. So it's actually only traveling 4r to get to the surface. So I can divide by m, and I can bring my dx across. So I'm going to get minus g r squared. It probably makes sense to bring the x squared up. X to the minus 2 dx is equal to v dv. And if I integrate both of these, I'm going to be starting at 5r. And you can see from my little diagram, we're finishing r above. That's the wrong way around. I'm starting at 5r and finishing r above. Let me just change them. I'm starting at 5r and finishing r above. So I can integrate that side. And with v, as always, between v and 0 to give me my velocity. So if I just bring the v over to the left, I'll have v. I'm going to integrate it, so it's going to be v squared over 2 and then minus 0. That's going to be equal to, well, let me leave it in integral form for a second. I can bring the gr squared, or the minus gr squared, outside, and I can integrate x to the minus 2 between r and 5r. So this is going to give me minus g r squared by x to the minus 1 over minus 1 between r and 5r. So that's just going to give me minus 1 over x. So minus g r squared by minus 1 over x. Bring the x to the bottom and it's a minus sign between r and 5r. That's going to be equal to my v squared over 2. So v squared over 2 is equal to, putting r in for x and 5r in for x, it's going to be minus g r squared by minus 1 over r, and then it's going to be minus g r squared by minus 1 over 5r. So this is going to give me, it's going to give me a plus here. So GR squared over R is just going to be GR. And we're going to have a minus and a plus inside. We're going to have GR over 5. Now, this looks like it's going to give me a negative. It is absolute value when we're dealing with these. So let's just get the absolute value of this. So it's going to be, if I create a single fraction inside, I'm going to get 5 GR minus GR over 5. Actually, it's going to just give me 4 GR over 5. We had a full one minus the fifth of one. So it's 4 GR over 5 is equal to V squared over 2. So V squared is 8 GR over 5, which would mean V being the square root of 8 GR, maybe small g, I've changed it to a capital for some reason, 8 GR over 5. That's the answer to this part.